이제 마이크 켰어요, 여러분. 이제 곧 시작할 예정입니다. 네.
시작했어.
네.
사운드 잘 들리시는지 테스트 좀 부탁드립니다.
마이크 테스트. 웨비나 곧 시작합니다.
소리 안 들려.
Hello.
조금 딜레이 있어요. 방금 켰어요. 한 5초.
한번 들어보세요.
자, 사운드 잘 들어오는지 확인 좀 부탁드릴게요.
사운드 잘 들어오나요? 사운드 체크.
여기 예? 소리 들려요?
들려 이제.
네.
오케이.
자, 그럼 이제 문 잠깐 닫아주시고요.
자, 4시 점검 웨비나 하겠습니다.
네. 네, 여러분 안녕하세요. 유니티 코리아의 프로덕트 마케팅 매니저 박주연입니다. 저희가 오늘은 좀 컨셉을 이렇게 잡았죠? 그냥 여러분께 좀 즐거움을 드리고자 이렇게 저희가 좀 재밌게 나왔고요. 저희 6번째 웨비나 이제 시작을 할 건데, 이번 주제는 지난번에 이어서 HDRP의 파트 2로 남은 이야기가 계속됩니다. 웨비나 시작하기 전에 잠깐 공지 드려야 될 사항이 있어서 먼저 좀 얘기를 드릴게요. 저희가 지난 2월부터 웨비나를 시작을 해서 유나이트 때 외부 세션으로 한번 만나고 이렇게 6번째 웨비나가 진행이 됐는데, 이번 웨비나를 끝으로 저희가 한 달에 한 번씩 정기적으로 찾아뵙는 웨비나는 올해는 당분간 좀 쉬어가게 됐습니다. 저희가 지난번 6번째까지 진행했던 웨비나의 컨텐츠를 잘 정리를 하고 저희가 웹사이트를 기획을 하고 있는데, 그 웹사이트에 잘 정리를 해서 여러분께 공개하는 시간을 좀 준비 시간을 갖기 위해서 당분간은 좀 쉬어갈 예정이고요. 저희가 재정비 시간을 갖춘 후에 내년 또는 뭐 빠르면 올해 하반기쯤에 다시 한번 정식 웨비나로 인사를 드릴 수 있도록 하겠습니다. 그동안 저희 웨비나가 없더라도 저희 지연님과 상윤님 에반젤리스트 분들이 하시는 라이브 스트리밍으로 가끔 인사드릴 수 있도록 하고요. 라이브 스트리밍 많은 시청 바라겠습니다. 자, 그러면 오늘 세션 이제 빅터 시작해도 될까요?
네네.
계속 이 모드로 하시겠어요?
네. 그럼
알겠습니다.
안녕하세요.
네.
유니티 코리아 필드 엔지니어 빅터입니다.
네, 이제 세션 시작될 거고, 오늘은 별도의 클로징 멘트 없이 빅터님 세션이 끝나면 방송이 끝나는 거고요. 저하고는 채팅창으로 계속 커뮤니케이션 하실 수 있고, 저희 웨비나 관련된 문의 사항은 제가 채팅창에 남겨드리는 저희 마케팅팀 주소로 문의를 주시면 감사드리겠습니다. 그럼 저희 세션 시작하겠습니다.
네. So yeah, this is like a continuation of what we did last time. So last time we did frame 1, 2, 3. So actually, if we check it, frame 1, 2, 3 is when we have frame 1 is like when we have the simplest configuration. It's just the deferred shader, and then frame 2 we have alpha test material, all the global illumination stuff, and for frame 3 we have forward and transparent material. We discussed the forward deferred hybrid architecture, and we also added some post-processing. So we use the post-processing Uber shader, right? So this talk will continue to make our frame more complex. So the first one, we will add Deckout. That's Deckout for both opaque and transparent objects. And then we will look at some optimizations that HDRP is doing internally. So we'll turn on those optimizations. The first of which is lightless building. So it's like the tile lighting stuff. And we also have a feature categorization where we try to make different variants of the deferred lighting shaders, and each variant is in charge of like doing different features. It's just another optimization that HDRP has. So let's talk about this again, right? So we'll add the cow, and then we'll add 2 optimizations. So this will be frame 4, 5, 6. After which we also will have little bit of subsurface scattering. So that's frame number 7. We'll not go deep into subsurface scattering. Okay, so let's do it. Frame number 4. So let's look at the settings first. Here now we enable the Deckout in the big HDRP setting, and we make sure to turn off this metal and ambient occlusion properties. If we turn it on, then Deckout will try to be able to modify even more properties, which will use even more memories. So we're just like keeping it simple so that Deckout only tries to modify some more basic properties. So Deckout is going to try to modify the color, normal, and smoothness of materials in the scene. In the actual scene, we will put some Deckout projectors in the scene. So we have 3 sets of Deckout projector on the opaque meshes. So the first set is only working on the base map, that's the albedo, and then the second is only affecting both the base map and the normal map, and third set of Deckout projector is going to affect base map, normal map, and mask map. This setting is just so that we can see more results when we actually look at the GPU capture. Besides these Deckouts working on opaque objects, we also have Deckout working on transparent objects. Now, like if you want Deckout to work on transparent objects, it's not on by default. What you need to do is you need to look at the Deckout projector component and tick this affect transparent tick box. The reason for us to have this trigger is because transparent Deckout is pretty expensive, so we don't want this to be turned on so easily unless you really want it. Okay, so this is the setup. Let's look at the setup in real life. Here is our scene. So these are the 3 sets of Deckout projectors that's working on opaque objects. Here you can see the Deckout projector, and here is another one. Here's another one. Oh, this is the box. Here is another one, and each Deckout projector uses some material that uses the Deckout shader, and we have 3 variants. The first one is doing something only on the base map. The second one is doing something on both base map and the normal, and the third one is doing something on base map, normal map, and also smoothness that's encoded in the mask map. And besides the Deckout projector working on opaque objects, we also have Deckout projector working on transparent objects. Look, this is a transparent bowl that we added in frame number 3, and you can see Deckout projector working on this transparent bowl, and that is because for this Deckout projector I have turned on affect transparent material. Yeah, so we added Deckout and we enabled Deckout in settings. Here's our new scene. Okay, so let's look at the theory. In HDRP, we have we keep a set of render textures called the DBuffer. It's called the Deckout buffer, right? The DBuffer, what does it do? It means what a DBuffer means is like, so here is your DBuffer, and each pixel in the DBuffer corresponds to a pixel in the GBuffer, and this pixel here means that I want to make this screen space position of the GBuffer more yellow, and this is saying like, hey, I want to make this pixel in the GBuffer more rust-like, right? That kind of thing. So a DBuffer is basically a way for us to encode modifications that we want to perform in the screen space. So how do we make it, right? So let's look at it, how we make it. we first do a full depth prepass for all the opaque material. So we make sure that in our depth buffer we have all our screen space geometry, and then we issue a instance raw call for each Deckout projector rendering to this DBuffer. So the draw call basically is these kind of boxes, right? You can see these boxes. This is the mesh we're drawing. These boxes. We're drawing these boxes. We're doing instance draw of these boxes onto the DBuffer. So we issue these instance draw call of the boxes. Now, these boxes is gonna generate a lot of fragments, a lot of fragment shader instances. And in this fragment shader, we find the screen space position of the opaque pixel it needs to modify. We can do this because we already have done the depth prepass. And then, knowing the screen space position, we can transform back to using the world view perspective matrix of the Deckout projector cube. We can find out what that screen space position is relative to the Deckout cube itself. Then we can decide the appropriate pending Deckout modification that we need to make to that screen space pixel, and the result can then be output to the DBuffer. I mean, for those of you that knows about deferred Deckout, this is basically very familiar. For those of you that are not, there is a paper about it for Warhammer like a few years ago. Just check it out. Or if you Google deferred Deckout on the internet, you'll find out. But like the only difference is, like in deferred Deckout, we modify the DBuffer directly, but in our case, we encode the modification first into a separate DBuffer. Okay, so now we have our DBuffer, right? And during the GBuffer pass, or when we are doing forward opaque rendering, we then look up the DBuffer to check what modification is needed for this screen space pixel and apply it accordingly in the GBuffer shader or the forward shader. Right. In our current configuration, the DBuffer has 3 render targets. One is recording the color modification that we want to make to each screen space pixels. One is recording the normal modification, and the final one is recording the smoothness modification. You may not be able to see this. This is actually a blue color. So this is the basic principle, but there are 3 details that I want to point out. The first detail is here. What if one Deckout modification is on top of the other? So in this case, like you have like the first set of modification here, and you also have a set of modification there. So on this pixel is both modified by Deckout set 1 and Deckout set 2. So we need to have the DBuffer encoding both the information of like both modifications mixed together. So how do we mix? That's the thing we need to think about, right? So if we go back to traditional deferred Deckout, what we are doing in traditional deferred Deckout is we are blending each Deckout modification with GBuffer directly, one after another. So when we use the DBuffer, we are blending each Deckout modification in the DBuffer, and then blending the whole DBuffer's result with the GBuffer. So these 2 operations should yield the same result. So how do we do this in a way that is like as if we are doing this? And the solution is to use a technique called alpha compositing. This is a thing featured in GPU Gen 3 Chapter 23, so you can go and check that. Basically, if you pause the video and check the maths, on the left is the operation that you usually do when you're doing traditional deferred deckout, and this is the operation that we do instead when we have DBuffer. So basically, the most important thing is the DBuffer not only has 3 channels, it also has the alpha channel, right? So we are using that alpha channel to get some extra information, and we use that extra information as well when we apply the DBuffer to the GBuffer or to the forward shader. You can check that the operation listed on the left is the same as the operation listed on the right. So by utilizing the alpha channel in the DBuffer, we make sure that we have correct compositing of the deckouts. The second problem we want to discuss is how does this work with forward shaders. So recall that in HDRP, if you want to render cloths or fur, that kind of thing, we use a complex forward shaders. We don't use a deferred rendering. So if we have those complex forward shaders, how does that work with the DBuffer? Like when you do a forward rendering, so if you only have a color modification, it's pretty simple. When you do the forward shader, you already have done a pre-pass. So when you've done the pre-pass, the Deckout system already knows the forward materials is there, right? So when you are doing the forward rendering, you can just simply look up from the DBuffer what modification you want to make at that screen space pixel and just apply it. But for normal, it's a little bit different, because let's look at these 3 facts. The first fact is forward material outputs normal in def pre-pass. Forward material do this because normal may be needed when we are doing pre-lighting calculations such as SSAO. So before lighting, deferred lighting, we want to know the normal and the depth information of the whole scene's opaque geometry. So that's why, right? We discussed this in the previous frames. The second fact is DBuffer is built after the depth prepass. You wouldn't be able to make the DBuffer without knowing the depth buffer. So this has to be true. And also, just after the GBuffer pass, the next thing we usually do is SSAO, screen space reflection, those kind of pre-lighting screen space calculations. And when we do these calculations, we need to guarantee that the normal and depth buffer are both complete. So if you look at all these 3 things together, then you would question, wouldn't the normal buffer just after GBuffer pass not reflect Deckout modification? And the solution to that is we use do an extra operation between the GBuffer and the DBuffer pass called Deckout normal patch. So the whole thing goes like this. In the depth pre-pass, if you have a normal material, you would do the depth pre-pass and write to the depth buffer. You will also write to the normal buffer. Next, you would do the DBuffer pass, where you draw all the modifications you want your Deckout to do to your screen space pixels. And then you would do a Deckout normal patch. The Deckout normal patch will basically just change the normal buffer that's already outputted in the depth pre-pass, such that it now reflects the normal modification that the Deckout wants to put. And finally, then we fulfill this, right? And just after the GBuffer pass, we have normal depth buffer complete, and that normal and depth buffer reflects the correct Deckout modification. An extra thing that we want to talk about is in order to minimize the cost of the Deckout normal patch, we are using the Stencil Buffer. So when we draw a decal, like when we draw the box that's bounding the whole decal projector, we will write to the Stencil Buffer that, hey, at this screen space position is a decal. Also, when we do forward material depth prepass, we will also write, hey, here is a normal, there is a normal outputted from forward material. So, and only when those two flags are both on, we will perform this decal normal patched operations. So like you can see, like this is where both are on, and this is where both are on. These are our rusty decals working on opaque materials, and these are our radioactive symbol decal working on our bowls. But you can see this is roughly like a cube, right? And these are kind of like a cube. It's the overlap of the cube with the scene geometry. And the third point that I want to mention, so the first 2 points is about some details in the debuffer so that it works correctly, right? So it works correctly when we have decals applying on top of each other, and it also works correctly when we have forward shaders. And the third point is about optimization. Besides just the debuffer, we keep a extra render target called the H-tile target. It's actually a very small texture. It's not using that much memory. And it's small because 1 pixel represents a 8xa tile on the debuffer. So it's like 64 times smaller than your actual resolution. And what this buffer records is if this tile, this 8 by 8 tile in the debuffer has some color modification, normal modification, or smoothness modification. So here is our H-tile, and you can see like it's mostly black because there is no modifications, there is no decal. But here there is some modifications in the debuffer pending to be applied when you're doing the G-buffer and the forward shading pass. Yeah, so this is our H-tile. And then when the G-buffer shader or the forward material shader look up the debuffer, instead of just doing the 3 texture fetch and realizing there's no change, you will first do an H-tile query to check out what textures really need to be fetched. So if you are doing let's say you're doing a G-buffer shader on this pixel, you would then query here and see, hey, like there's no flag, so I don't need to care about decals. And if you're doing a forward material shading on this screen space position, then you would find out from looking up the H-tile that you would need to modify everything. You would need to modify color, modify normal, modify smoothness. So you would do all the lookups for all the 3 debuffers. It's like a lookup table for the debuffer textures. So 3 things already said, and okay, let's talk a little bit about the design. We've talked about this. So the most well-known way of implementing decal, if you have a G-buffer pass, is screen space deferred decal. That's featured in SIGGRAPH 2012. This is a screen space decal in Warhammer. Now, yeah, we already talked about this as well, right? So traditional screen space deferred decal is you do the G-buffer pass and copy the depth buffer to a texture, and then each decal issues a draw call of its oriented bounding box to the G-buffer, and each resulting fragment can appropriately decide what modification to the G-buffer it should apply by sampling the depth buffer, and then apply the modification it needs to G-buffer by blending. So here is a blending. We use blending to modify the G-buffer. But there are some disadvantage to traditional screen space deferred decal. firstly, it doesn't support applying this on forward opaque material. You are modifying the G-buffer directly, and if you have forward materials, it's not on the forward material does not care about the G-buffer. So modifying the G-buffer will not really be able to affect how forward material shades. So we need to actually have the debuffer to record what modification we want on a screen space pixel, so that the forward shader can later look up what needs to be done. And the second point is it constrains G-buffer layout, because we are changing the G-buffer by blending. So the whole thing must be blendable, so we can't do complex encoding. You remember that we have normal encoding in our G-buffer. That would not be possible if we do traditional screen space differ deckout. And we also constrain storing data in G-buffer alpha channel. HDRP is about visual quality, and we very much want to keep the forward differed hybrid architecture. So we use debuffer. It takes more memory. It gets everybody to do def prepass, and it introduces more texture fetches. It introduces more passes, but it's got higher quality. Now, so far we only talked about Deckout working on opaque stuff. So what about if we do transparent pixels? So what we do is we use a separate system. There is very little overlap between Deckout for transparent stuff and the Deckout system for opaque stuff. In the transparent Deckout system, we treat each Deckout as if it's a light. So we upload to the GPU the color normal smoothness map to a Deckout atlas. So in this case, we are doing some color modification, right? So we are just uploading that stamp that we want on the color to this huge Deckout atlas, and then we also upload to the GPU the Deckout Projectors transform data and the Deckout atlas key. So knowing the Deckout atlas key, you will be able to find out I would want to sample this sub area of the whole Deckout atlas for color modification data. So this is very much like uploading to the light list, except that it has an extra reference to the Deckout atlas. And when we are rendering transparent material, usually when we're rendering anything, you loop through each light and see how the light adds illumination to your pixel. And with Deckout Projectors for transparent objects, you do the same. So you not only loop through light, and then you also loop through the Deckout data array, and for each entry modify the fragment appropriately. So one thing to note is transparent Deckout is as expensive as a light. So, and more so actually, because it's fetching texture data. So that's why we have a tick box for it. Like if you don't tick the tick box in the Deckout projector component, it won't be turned on accidentally. Okay, Deckout finished. I consider this the hardest frame. It's very hard to explain. Okay, next is frame 5. So frame 5 and frame 6 are optimizations that we are starting to do. Before that, let's revise what we talked about in theory by looking at the actual frame capture. So this is the scene that, okay, how do I look at the scene? The final rendering result looks kind of like this. Wait, not this one. Let me try. We're looking at frame number 4. Okay, so this is our scene where we added some Deckout modifying opaque materials and some Deckout modifying transparent materials. And if we do a frame capture, so let's go through things very quickly. It should also help us recall what we did the last 3 frames. The first thing I want to say is once you enable Deckout, you do depth prepass for everything. So in the last frame, we only do depth prepass for alpha tested material and forward materials, right? But if we want to do Deckout, before the DBuffer pass, we need the DBuffer, and the DBuffer needs depth information. So first off, everything gets a depth prepass. So here is, you can see everything being drawn to the depth buffer. We have a depth in Stencil Buffer, and we're just drawing to that depth in Stencil Buffer, drawing. So this is our ordinary geometries also being drawn there. And of course, we also draw the grass. The alpha tested material is also drawn in the depth prepass. And finally, the very last one is our forward material, right? And besides drawing to the depth in Stencil Buffer, it also draws to the normal buffer. As you can recall, forward material draws to the normal buffer as well in depth prepass, and that normal is used later just after G-buffer pass to perform screen space pre-lighting calculations such as SSAO. So we're doing it here. Now we've done the depth pre-pass. The next thing is a compute shader. What is its name? It's called stencil copy. This is just copying out the depth buffer from our rendering result to be used as a texture later. That's not important. The next thing is the actual DBuffer render. So you can see that we are drawing to 3 render targets. The first render target is the color. Second is normal. This is gray because normal is a vector. This is the mask. So here it records smoothness modifications. And we're just we're just drawing boxes and sampling the depth texture we generated here and checking what modifications we need to do on each screen space pixel. So here's the first set, second set, third set of modifications. Here we've done alpha compositing, and then everything is being drawn. Now we have finished generating the DBuffer, and you can also see that we have where is our H tile? Right, so here is our H tile. You can't see it. Let me make it clear. Okay, here is our H tile. It's the lookup table to speed up the buffer lookup. Okay, finished. Next is we've finished generating the DBuffer now, and this is the DBuffer normal patch that we talked about. So forward material has already generated its normal here, but the normal may want to be modified by the Deckout. So we are patching the normal modifications on top of the normal buffer right now. You can see. Yeah. And then next is the G-buffer pass. It's a very run-of-the-mill. Let's go to the event view. Now it's the G-buffer pass. We're drawing the G-buffer. You can see, like, as we draw to G-buffer, the Deckout is applied as we draw to G-buffer. So this guy, right? So we are drawing a ball, and the ball being drawn already look up from the DBuffer what modification it needs to take, and so like the modification is applied to this. So we're going through drawing the G-buffer, as also applying the DBuffer's modifications using alpha compositing, drawing the grass, and so on and so forth. So the next thing is we generate a bitmap from the depth buffer. This is so that we can have a bitmap of the depth texture, maybe later useful for SSAO or SSR or other things. So this is our SSAO calculations, and this is our SSR calculations. We talked about it last time. We're not going to talk about them anymore. The thing we want to, if there's anything to talk about them, is that in this frame, they need the normal buffer, right? So, and that's why we need the forward shaded material to output its normal, which is why we now need to do the Deckout normal patch. Now here, finally, we are doing a deferred lighting. This is just a huge fragment shader that shades everything, and then we're doing post-processing. Yeah, everything's done. So if there's anything special about it, it's about this DBuffer generation, and in the GBuffer we are looking up the DBuffer. There's a Deckout normal patch for the forward material, and finally, when we are doing the opaque forward draw, that's our silky bowl, this code, right? We are also doing we're not doing deferred shading, right? This is a forward shading, and this forward shading looks up from the DBuffer here, right? Here is our pixel shader, which is doing forward shading. This is drawing the silky bowl, and one of the texture it uses is these guys. These are the right. These are the DBuffer, right? So again, when we are doing forward opaque draws, we look up from the DBuffer. This is possible because we use the DBuffer instead of just doing traditional deferred Deckout. Okay. Next, frame 5. In this case, we haven't really changed anything about the scene. All we changed is the setting. So previously, we turned off everything under the light loop and async compute setting. Now we turn on async compute, and we turn on the light loop, big tile prepass, and deferred tile option. So this is all the changes, right? So let's look at the theory. So let's assume that this picture is our screen space, and this is a spotlight, and the spotlight does not affect anything outside of this area. And this is another spotlight, here's another spotlight, and here it's like a point light, right, with a radius, and everything outside of this radius isn't really affected by the light. It is way too weak to be significant. Now, we are shading, let's say, this inside somewhere here. Then, in all the previous frames, we upload a global light list. So, light number 1, light number 2, light number 3, light number 4 to the GPU. And when we are shading here, we are looping through each of the light and seeing how each light affects this pixel, which will be nothing. It will affect in no way. So this is like expensive operation doing nothing. So we will want to avoid it. In previous frames, for each fragment, we loop through every light in the scene. The tile lighting is a technique that avoids doing lighting calculation for lights that doesn't affect fragment. So let's look at tile lighting first. Now, first, there's lights in the scenes, and what we do is we not only upload the lights only, but we also upload a bounding volume of the light to the GPU. And on the other hand, so first we make sure we have the depth buffer with opaque scene geometry, and then we divide the camera frustum into many small tiles. So this whole big trapezium thing is the camera frustum, and these like thin trapeziums are our tiles. So we divide the camera frustum into many small tiles, and for each tile we find the maximum and minimum depth value. So on this tile, like there each fragment, we have the depth buffer, right? So we can find out like maybe the actual opaque geometry is like this, right? And then we find the minimum depth value and the maximum depth value. And because we know this bound on the x and y, and we also know this bound from the z dimension, this actually makes us a bounding box. And for each fragment that's shaded inside this tile, these fragments must be inside this bounding box. So if a light has this bounding box and a tile has this bounding box and they don't intersect, then this light is irrelevant when we are shading fragments in this tile. For each tile, we find light potentially affecting fragments shaded within the tile by performing intersection test between the light bounding volume and the tile geometry bounding volume. This gives us a tile light list for each tile, and when actually performing lighting calculation for a fragment, instead of going through the whole light list, we go through the appropriate tile light list. So tile light list is different for each tile. It's not a global light list. It is a list of light that affects the tile. So if we go a step further, and there is an extra technique that we're using called fine pruned tile lighting. Fine pruned tile lighting is a version of tile lighting where we really do our best to minimize the size of our light list. So most important difference is that we just do the same as tile lighting, but after we generate the tile light list, right, we do an extra pass to prune the original tile light list. So what is that extra pass? For each pixel in the tile, we find its depth value. We can do it because we already have the depth buffer handy. And then we find the list of lights whose bounding volume includes x, y, z. So each pixel, we're looping through the screen space. X and y are increasing from 0 to maximum values, and we look up the depth value. Then we are really looping through every pixel in the screen space geometry, and we're finding the list of light whose bounding volume includes these pixels, and we merge these lists to get a pruned tile light list. So here's our tile. This tile will actually contain a number of pixels, and for each pixel, here is the tile pixel here, here's the tile pixel there, and this pixel has XY here, and by looking up the depth buffer we can find out its Z value, so it's this position, and it's only really lighted by this like round light, and so everybody else is not in the list. And every pixel inside this tile will have such a list, and we just merge these lists across each pixel in the tile. And this is our pruned tile light list. So the point is that suppose our light bounding volume is perfectly tight. That means if it's inside the volume, it's affected by the light. If it's outside the volume, it is not affected. It's not a bounding box that's got some extra spaces. Now, suppose it's perfectly tight, then fine prune tile lighting ensures each light on our pruned light list at least really affects one fragment in the tile. So it's in a way perfect, but it's expensive because we are checking the depth value for every pixel in the tile, for each tile. So yeah. So this is tile lighting. Tile lighting only really works on opaque geometry because tile lighting assumes that we only render fragments at screen position XY with depth value sample depth buffer XY. So tile lighting does not work for transparent stuff, right? For transparent stuff, we use another technique called cluster lighting, which is very similar. So for cluster lighting, what does it do? For each light, we define a bounding volume. So and then we divide the camera frustum along all 3 dimensions. So we previously only divided it across the X and Y dimension. Now we also divide it across the Z, the depth dimension. So we get these clusters. So this is a tile in a camera frustum, and here is a cluster in the camera frustum. Now we have a cluster, which is a bounding volume. We also have the light bounding volumes, and then we can similarly perform intersection test. And if a light bounding volume doesn't intersect a cluster, then that light is irrelevant to that cluster. Okay, so this is the big theory about all this, and here is us going through the actual shaders in HDRP doing all these light list building things. So there is first we build the light bounding volumes in CPU. So we're making abstract geometry bound of each light. If it's a point light, there's maybe a sphere bound, and so on. And then we upload those informations to the GPU, right? So now, from then on, we're doing compute shaders. We are first making a screen space AABB for the light bounding volumes. This is in order to AABB tests are very fast. So besides having the light bounding volumes, we have a AABB for each light. That's a bigger box. We first do AABB tests, and only those that pass the AABB test, we do further finer tests. And from those, we generate a coarse light list for each tile in the for each big tile in the scene. And this coarse light list is further pruned in 2 ways. First, it's used to generate the fine pruned tile light list, and second is used to generate the clustered light list. So these are candidates that we use, and then we further prune them. These are then used when we're doing opaque rendering, and these are used when we are doing transparent rendering. And this ensures in the end that when we're doing opaque, we loop through less light, and here when we're doing transparent raw coarse, we loop through less light. Okay, so this is actually I'm going through 1, 2, 3, 4, 5 each step a little bit. So this is pretty text heavy stuff, so if you need, please pause the video and just read the text. But I'm still gonna go through it with my mouth. So build light bounding volumes. So there are 2 types of light bounding volumes that we upload. First is a simple description that works for every light. So it doesn't matter if it's a point light or spotlight or whatever light. We will try to bound it with a trapezoid. So this trapezoid is it's like a cube, but you can change its this dimension and that dimension as well. So there is 5 degrees of freedom: height, X, Y, and then how much you shrink in the X, how much you shrink in the Y direction as you go up. So it's here. And we also upload a bounding sphere. That's also the same for all the light types. So for all the light types, we universally have a bounding trapezoid and a bounding sphere. And then next, for particular to each light type, we have a tighter bounding volume. So for example, if we have a point light, then we have an ellipsoid that's exactly bounding the point light. So actually there's 3 things uploaded, right? Trapezoid, bounding sphere, and tight bounding volume. So this is step number 1. Step number 2, we are trying to make a loose, big but easy to calculate bounding volume in screen space. So we're trying to generate screen space AABB bound for each light in the scene. For every light, we clip each face of its bounding trapezoid remember trapezoid is this guy. So the bounding trapezoid in world space is clipped, and then clipping is complex but necessary for cranes. So if the bounding trapezoid has some intersection with the camera frustum, we need to make sure that it's exactly that shape in the camera frustum before we transform the world space into perspective clip space. And after we do this clipping, we may not have a trapezoid, but it's still going to be a convex volume. And this convex volume, let's say it has vertices V1 to Vn, we can then use these to generate a AABB that includes the minimal AABB that includes all these vertices in screen space. And this will bound the light and is easy to work with. Here is it, this pass, this compute shader actually, when we look at the GPU capture. And the third step is the coarse light list generation. We divide the screen into many 64 by 64 big tile. And for every big tile, we find all the light with screen space AABB overlapping the big tile. So this is very simple, a screen space 2D test. And the next thing is we prune away the light with bounding sphere not overlapping the big tile. So this is a world space 3D test, but it's still okay because we are doing a test with bounding sphere, and bounding spheres are simple. And for each of the big tile, we get a coarse light list. So coarse light list generation is simple and fast, but still effective. So here is this being done in real life with a compute shader. The final steps, if you're doing opaque rendering, is the tile light list generation. So the tile light list, our tile is smaller. Big tile is 64 by 64, and actual tiles is 16 by 16. For the smaller tile, right, we've sampled the depth buffer to get the max and min depth value for our small tile. So knowing this, we can have a bounding box for all the fragments inside our tile. We take the coarse light list generated from last pass of the big tile that contains this small tile. We prune that coarse light list using AABB of the light and AABB of the tile. This is very simple screen space 2D. And then we further prune using bounding sphere of the light and AABB of the tile. This is world space 3D. This is actually the same test that we do in the big tile, but with a smaller tile. This is not expensive, so we are doing it again with a smaller tile. And then here comes the expensive bit, right? So for every fragment in the tile, we perform a tight bounding volume inclusion test. The tight bounding volume is this guy. Tight bounding volume is different for each light types and is very tight. And we are doing a tight bounding volume inclusion test for every fragment in the tile to see if that light is really illuminating that particular fragment. And then we remove light not intersecting any pixel in tile. So the last step is expensive. It involves a lot of depth texture fetch. So we prune a lot with cheap method beforehand, right? The cheap methods being 4 rounds. 1, 2, 3, 4. Okay, so this is how we generate a light list for opaque stuff. Now, for transparent stuff, we don't do tile lighting, we do cluster lighting. So how do we do that? A cluster tile is a tile, you know, like there's a lot of clusters, and some clusters belongs to the same tile. So we call each of those cluster tile. So we're now just doing 2D stuff. We're not doing it, we're doing it very much like tile lighting up to this point. So for each 32 by 32 cluster tile, we take the coarse light list from last pass, and then we prune the coarse light list using AABB, 2D screen space test, and then we're doing 3D test of AABB with bounding sphere. And then with these pruning, which is we will get a candidate of lights, a list of candidates, light candidates that could affect fragments inside a particular tile. And then the next thing is for each cluster in our cluster tile, so this is like our big cluster tile has a lot of clusters, and we are now doing it for each of the clusters. So actually, right, so this is a cluster tile, and these are clusters in a cluster tile. I think that should explain it. Okay. So for each cluster in our cluster tile, we take the cluster tile light list, we prune using bounding trapezoid of the light, and the cluster we do the intersection test in world space 3D, and this will give us our cluster light list. So here is our lighting list generation, right? This whole process. Now we prune a lot, right? So however, if we're on DirectX 11, then it's okay. DirectX 11 supports async compute. Compute work and draw call can happen at the same time. And yeah, light pruning compute shader, that is this whole pipeline, is computation heavy. So we're doing a lot of like add, multiplication, this kind of thing. On the other hand, shadow mapping, when we are trying to do cascaded shadowing, this kind of shadow mapping is the fragment shader doesn't do much. It is really just mostly doing rasterization. So rasterization uses the rasterization unit in your GPU, and calculations uses the floating point units in your GPU. So these are using different resources in your GPU, and if we can make them do things in parallel, it would be really good, right? It would have great parallelism. So with DX12, this is possible. We talked about this in the GPU Gem 7. However, on DX11, we don't have async compute, and this aggressive pruning may not be as necessary if you do not have a lot of lights. And it can itself be a performance burden, especially tiled fine pruning. So we are aware of this, and we are working on better ways to deal with this. In the meantime, you can try to fiddle with the HDRP settings, and if that doesn't work, you can modify a little bit about the HDRP code. It's the HDRP code is very readable. So yeah. So like if we look at the GPU capture, you will see that the fragment shading time is shrinked quite a lot. Okay, so let's look at the actual capture. Yeah, I think this session is going to be like 2 hours. Right, so it's basically the same thing, right? Mostly the same. The only difference starts when we are generating the light list. Build light list, this part. Okay, so build light list happens right before we do our deferred lighting. And it's gonna do it after our screen space pre-lighting calculations. That's SSAO and SSR stuff. And there are a few steps which really corresponds to the picture that we have in the PPT. So first, screens bound this compute shader, screen bound AABB, that's generating the screen space AABB for each of the lights. So recall that this is us having uploaded the bounding trapezoid of each light, clips it in world space, and then using the vertices of the convex volume generate a screen space AABB. Now with this data structure in place, we do the big tile list generation. This is us looping through every 64 by 64 tile in the screen space and checking with some simpler tests what are the potential lights affecting that big tile. This is light list build tile light list generation source big tile. So this is taking the big tile as source and generating tile light list. This is the FP fine prune tile lighting, pruning, and light list building operation. And finally, this is a source big tile tile light list generation clustered. So this is doing the clustered light list generation. And with this light list, we are doing the same whole screen fragment shading. Now, it's not yet a compute shader. It will become a compute shader in the next frame. But this is still a big whole screen fragment shader of a quad across the screen space. And as you draw the quad, you would sample the DBuffer and loop through the light list to check for illuminations. But in this particular case, what is different is instead of looping through the global light list, you loop through, you know where your screen space position is, and from that you will know which tile you belong to, and then you can look up the correct tile light list. So you are looping through less lights. And this is our forward opaque core, and when we're doing forward opaque rendering, the same applies. So here we are doing a forward shader of some geometry, and each fragment in that forward shader draw, you would know your screen space position, and you can know which tile you belong to, and you can check your tile light list. So this works not only for deferred rendering, it works for forward rendering as well. And not only it works for opaque, it also works for transparent stuff. So when you're doing transparent stuff, you will know your screen space position, and because it's forward draw, you will even know straight your depth value as well. And from that, you will find out which cluster you belong to, and then you will find the light list, the list of lights that should be affecting your cluster. So you are looping through less lights. Yeah, great. Okay, next is frame 6. This is going to be a bit shorter. So we enable here compute light evaluation and also compute light variance and compute material variance. So what does this do? Let's look at a problem first, and this is the solution for that problem, right? So let's look at the problem first. When we do deferred renderer in general, the deferred shader starts to bloat because the scene data you can access comes from the DBuffer, and you use the same shader to shade every variant of things. So the lit shader supports a lot of lighting models. There is the standard opaque, there is the standard transparent. We also have a anisotropy mode, SSS mode, iridescence mode. These are like some special mode that we haven't talked about in this talk. But the lit shader is even more versatile than this talk's being showed. And so the lit shader has a lot of modes, right? And on the other hand, the light loop deals with a lot of different kinds of lights. We have directional light, spotlight, point light, area light, environmental light. So with a lot of light variations and material type variations, it's hard to avoid in the shader a lot of branching. So if your light is directional, there is some special logic for directional stuff, and if your mode is something, there's some special logic. So these conditional logic will start to crop up, and if you look at this picture, it explains why branching is bad. A GPU compute unit has only one instruction fetch. So, you know, like every thread in your compute unit needs to be on the same code. So if you are doing branching, here is if A, if B, else, right? If you are entering into the if A, and some of your thread is doing the A logic, the thread that actually should be doing the B logic will just do nothing and wait for the thread that's doing A logic to complete. And therefore, if you branch with 6 line and 6 line, then you will actually do a total of 12 lines. If in the same compute unit you have 2 threads taking different paths. So although branching is not always super expensive if your compute unit has threads all taking the same path. So although branching is not always expensive, if 2 threads working on the same compute unit has divergent conditional branch, then the shader performance will suffer. So when we're doing a whole screen shader pass, you know, like when we do this huge fragment shading across the scene, when we do deferred lighting, there's no guarantee that similar branching behavior is going to be grouped in the same compute unit in the GPU. So now we are doing already fine prune tile lighting, so we already have the concept of tiles. On top of this system, we can categorize how each tile is like. So what light is influencing the tile, and also what type of material is in the tile. So this is an example. It's coming from Garawani, a paper from Garawani in 2016. Now our tile is 16 by 16 pixel, and it's not too big, and it's reasonably likely that there's only one type of material and one type of light covering the whole tile. So we can reduce, we can stop considering all the other conditions. Now with this data structure, which categorizes the tiles by light type and material types, we can then have a system that utilizes this data structure to do things better. So what is that system? Let's look at it. So this is a lot of code walkthrough. So we're going to go through this walkthrough. So the lit shader is the deferred shader in HDRP. It has a great understanding of DBuffer, and it has a lot of mode. So we are now making variant of the lit shader. So imagine the lit shader being a mega shader, but some of the code may be useless because it supports some features that we are not using, and then we're gonna just like comment out those unnecessary parts. And by commenting out various unnecessary features, we get reduced variance of the lit shader. So this is a table in HDRP. It's in lit.lsl that lists all the variants of a lit shader that we will generate. So this is lit shader with these features, right? Some light feature and some material feature, and every other features, the code supporting those features, we will strip out. So this is what it means. So we have variant 0, which supports only these features, stripping out the other unnecessary codes. And similarly, we'll just do the same for from 0 to 17 and more. Actually, this is not a screenshot of the whole thing. There is more variants. Now, this table is supposed to increase in complexity as we go down. So this is very simple and more complex. Here is a function that loops through this table and find the first variant that supports the feature you want. So here you give this function feature flags, and it's like saying, hey, I have a point light and no spotlight. I am doing subsurface scattering, but I'm not doing anisotropy. This kind of thing is encoded through a feature flag, and by giving this function gives you back a variant, a variant index that supports your features. And basically what it's doing is just looping through this table to check the first variant that supports this feature. Now, okay, so now we have a way to, we have a system where we can ask for variants supporting particular material and light features. Now, how do we get this feature flag, right? The next question is. Here we list a tile each compute shader variant should cover according to the tile's feature flags. So before we talk about where the feature flags come from, let's talk about how this is used. So here we have a variant, and the variant is so we are doing tiled lighting, and we will have a variant, and we will basically have this G tile list, which is a list for each variant and what tile that variant is responsible for shading. Right. So this is a list for each variant of tile indices, and these tiles has a certain these tiles are the tiles that this variant is responsible for shading, right? Okay. Now, where does the feature flags come from? A tile's feature flag is queried from a global list called gtile feature flags. This is just a dictionary from the tile index to the feature flag value. So the next question is, where does this feature flag get built? The first thing is we already know what light is in which tile because we are doing fine pruned lighting. So fine pruned tile lighting. So when we are building the light list, we already know for each tile what light is there. So we simply just take all the types and encode that for your tile, right? So this is being done at the end of light list building. And the material feature flag occupies 3 bits in the alpha channel of GBuffer number 2. So this is our GBuffer layout for a standard mode of the lit shader. In GBuffer 2 alpha channel, the first 3 bits, we encode the feature ID, which is flag saying what type of material there is at that particular part of the GBuffer. There is a pass that we do. We have a dedicated compute shader pass that collects the GBuffer material feature flags for each pixel in the tile, and then bitwise all of these things, of these feature flags for each pixel, and then we will record the resulting what material feature is used in the tile flag in G tile feature flags. So tile feature flags is first being written by the light list building part. Here, as we build the light list, we tell this global variable what tile, for each tile, what kind of light it has, and then after that there is an extra pass that checks the GBuffer for material types, and from that it also writes to this same table, and after this you have a complete data structure here, G tile feature flags. And with that data structure, that is going to the feature flag variable. The feature flag variable goes to feature flags to tile variant, which gives us a variant that supports this feature flag, and that variant, and then we write to gtile list, which is a list for each variant what tile it needs to draw on. And the final result is a series of compute shaders. So previously we are doing a huge single fragment shader across the whole screen. Now we're dividing the screen into tiles, right? And then we have a number of variants, and we just do compute shading with each variant. And the variant A is going to look up what tile this variant is responsible for drawing on, and maybe it's nothing, so then it would take a very little time. And sometimes you have this like variant of the lit shader that has a lot of responsible tiles, and then it would just draw on all those tiles, so it takes a long time. In this particular case, we have two variants drawing a lot of tiles. Basically, the tile is divided between these two variants to be drawn upon. So when you're using HDRP, a idea is to modify the table K feature variant flags in HLSL, so it categorizes features better for your particular project. Maybe there are some features that your project doesn't even use. Maybe there's no hair or something. Wait, this isn't too maybe you don't have anisotropy, let's say. Then you can like take away all the anisotropy material flag stuff. So just you can modify this table is what I'm saying. Right. Okay, let's actually look at the GPU frame capture now. Oh my God. So the thing we'll look at is build light list. So this is very similar to what we did last time. Just like last time, we first do calculate the screen space AABB of bounding trapezoid of lights in the scene. And then we generate our big tile list. This big tile list is further pruned for tile lighting here. Now this is the same path as last time, but the behavior is a little bit different. At the very after we generate our tile light list, our fine pruned tile light list, we also make sure we maintain the variable that records what tile has what kind of light. And then we generate the clustered light list. This is the same behavior as last time. And here is a extra compute shader that was not there last frame. And this compute shader is called material flags gen OR. It's doing a bitwise OR for each tile. For each tile, you're just looping through every pixel in the tile and checking the GBuffer for material feature flags, doing a bitwise OR over every pixel. And what you get as a result is what type of material is being used in a tile. Now this is a little bit different as well. We need to do a build dispatch indirect. What that is doing is it's building a structure telling the shader variant what tile is responsible and how many threads it needs to spawn in order to draw these tiles. So we are building doing some preparation work so that we can tell each variant of the lit shader what tile it needs to be drawn and how many tiles it has to draw on. So now we are starting to actually draw. We're actually starting to use the variant. So this is variant number 0. This is variant number 1. This is variant number 2. So these are different variants of the same lit shader. Each has some feature being stripped off. It maybe some doesn't support point light, maybe some doesn't support anisotropy. So those are some simplified version of the lit shader, and there are like a lot of them, and we are just looping through each of them, and each of them knows which tile they are responsible for drawing on and how many tiles they have to draw on, because we did the build dispatch indirect compute shader pass, and so we're looping through all these guys. And these are two dominant shaders. So in other words, variant 3 and variant 4 is responsible for drawing a lot of tiles, and then we're looping through all the variants, and in the end we get the all the variants being drawn upon. Yeah. So in the end, the advantage of this is that it makes sure that we group our shading in such a way that similar things get done in the same compute unit, and also we ensures that unnecessary branching operation is not being performed. Okay, so if you look at this thing, you can see like this is a long bar and this is a shorter bar, which means that it's good. Okay, final frame. So this is basically us going through all the more fundamental part of HDRP. There are parts we skipped, like we didn't talk about motion vectors, we didn't talk about temporal anti-aliasing, but like the very fundamental things we kind of covered. We also didn't cover deeply about transparent stuff. That's a shame. But let's look a little bit about the more advanced features. So the advanced feature I picked here is subsurface scattering, because it has a stronger relationship to the core architecture of HDRP, because it forces the HDRP to do split lighting. We'll explain that later. So let's look at subsurface scattering. What so the setup, right? The setup is that we enable subsurface scattering in our settings, but there is also transmission, which you can enable. But we are not enabling it to simplify things. And we have removed our 4 red balls, right? We used to have 4 red balls. Now there's just 2 subsurface scattering balls. The ball on top has SSS material with subsurface mask value being 0. That's in order for it to have a weak scattering. And the ball underneath has a surface scattering material, and the subsurface mask value is 1. It means it has a strong scattering. So let's look at the scene. Where is our ball? Here we go. So here is our SSS material weak scattering. Here is our similar strong scattering. It's just is there right? So what is there to show is that previously, we always just use the standard mode. These are the flags. These are the things that represent material variant. So there are these, and these are going to be the flags that we put in the material type in the last frame, anyways. And when you look at a lit shader material, we always use just standard, but now we are on surface scattering. That's what I want to show. Okay, and we also turn it on in the setting. So theory. So direct diffuse. What does diffuse mean, right? Specular means a light touches the surface and bounces right back, and diffuse means that the surface absorbs the light and then re-emits it. So here is the light coming in, and it's like, hey, bouncing a little bit and then coming out to the camera. And if it's coming out here and coming in here and coming out at the same pixel, which is likely because like it cannot travel very far in the surface, right? If this is 1 pixel, then this is what we call a direct diffuse lighting. Now, suppose a light travels into the surface but it bounces like somewhat luckily into a different area and then it comes out. And what about this behavior, right? This behavior is like happening commonly in like less dense materials like skin or leaf. This is called surface scattering. And what about if the light goes into a point and travels a bit farther than 1 pixel and come out from even the other side? This is what we call transmission. HDRP supports transmission, but we're not going to talk about it to simplify things. So our diffusion behavior is encoded in a diffusion profile. So this is a scriptable object, and it stores a subsurface scattering configuration. So for subsurface scattering, this asset specifies how much light from one place is transferred to another place during the SSS pass. So suppose light comes in here. This is saying the likelihood of this light going to here is high, and going there is like lower, going there is even lower. How does the likelihood of a light traveling from this point to other points vary as we increase the distance? And this is a spectral value, so it's different from for R, G, and B. So in this case, you can see the red light travels far. So the red light coming here is still quite likely to reach this point, but the blue and green light, they travel not as far. So they are kind of constrained within this small radius. And so this diffusion profile specifies this light scattering behavior as we vary the distance. But programmatically, it not only contains this information, but a lot of pre-calculated information that helps us speed up the SSS calculations later. So you may ask how this picture is generated. It's a radial symmetric picture, and so we just need to know how a light intensity changes as we change the radius, and that is governed by the Burley's normalized diffusion model equation. It's quite a more intuitive model. R here is the radius, so as we change the radius, you have a different output value, S is a parameter that we can change, and A is a normalizing constant. So we have 1 degree of freedom. It's a class of curves as we vary S, or equally as we vary A, right? We can vary A, and then S then will be determined by normalization. Again, if we look at Stencil Buffer, you can see we use Stencil Buffer quite a lot to make sure we don't do unnecessary calculations. In the GBuffer pass, if a lit shader is in subsurface scattering mode, it tags the stencil with the split lighting flag. So previously we have a lighting flag. So if we have a lighting flag, it means that this is not sky. A sky with no like actual draw core being up on top of that is no lighting. And then whenever there is draw core, there is lighting, right? But there is actually a third lighting flag called split lighting flag. So in the previous case, we only have no lighting and normal lighting. But now there is a third flag called split lighting flag. It means I'm not only lighted, but I also want subsurface scattering. Next step, when we're doing deferred lighting, for pixels tagged with this split lighting flag, we have usually we just do the deferred lighting, and then we find out what lighting that pixel should receive, both the specular and the diffuse value, and then the sum of the specular and the diffuse is going to be outputted at this like intermediate buffer, this lighting buffer, let's say. But in this particular case, when we have subsurface scattering, there are particular pixels where it has a split lighting flag, and if you have a split lighting flag in the stencil shader, when you do the deferred lighting, it outputs the diffuse to a separate render target. So here is all the diffuse lighting. So diffuse lighting includes the direct diffuse that you specify from your shader, and it also includes the indirect diffuse that's coming from light map, light probe, and the sum of those, the diffuse lighting, is recorded in this separate render texture, and the specular part is outputted here in your usual buffer, the usual buffer that you output to during deferred lighting pass. And do not be confused by this. This is actually not yet drawn. The color here is from last frame. So you can think of this as completely black. And this is kind of dark, but it has the specular lighting. It's just really weak because this is a very diffuse, heavy material. So again, right, we are doing deferred lighting. And this is like this because we are doing material and light categorization and tiled compute. So we're doing different shaders for different tiles. And so here is like a group of shaders of a shader variant of the lit shader, right? And here we output the diffuse lighting in the separate buffer, and the specular lighting is drawn here. Yeah. And this is happening because we tag the stencil buffer, so that and we ask HDRP to do split lighting, right? The diffuse and the specular light is split into different buffers. And why would you want split lighting, right? The reason is that screen space subsurface scattering only works for diffuse lighting. If you do subsurface scattering on specular lighting, it will be wrong. So now we not only output the diffuse lighting to a separate buffer, we also square root the color the light picks up from the surface. So you can see that this guy is looking less colorful than the color last frame. It's because the color that we add to the illumination from the surface is square rooted. So the lighting, the illumination intensity is not changed. The thing that's square rooted is only the color. That's the albedo map. It's the brightness is not changed, but the colorfulness is square rooted. And this is like yeah. And then next thing is that we transfer light around the surface in screen space according to the diffusion profile. So what we're doing is we're taking this diffuse lighting thing with surface scattering. So this is all the pixels here has diffuse lighting of material that has subsurface scattering. And we're taking this buffer and transferring energy between pixels. So suppose we are now shading this pixel, we sample the light energy coming from around it, and we also know the depth buffer and normal buffer, so we know the scene geometry. And according to the scene geometry, we also know the color value of the buffer beside it, because we have the G buffer, right? So we know a lot of stuff. We know the diffuse color of the pixels around it. We know the depth value. We know the normal. We also know the diffuse lighting that this has received initially. And then we are just transferring, we're sampling around this guy and then taking some kind of average, and the average value being outputted. And this kind of thing is quite complicated, and how it's being done is a lot of it is encoded in the diffusion profile. You remember the this scriptable object, this diffusion profile. It does a lot of pre-computations so that we do this like energy transfer efficiently. Now, after we get some kind of energy transferred illuminations, we then take exit lighting colorization. So when we calculate the result after the energy transfer, we then multiply this by square root of the color of the exit pixel. So when we're drawing this, we take the square root of the pixel that absorbs the light. And when we're doing this pass, we take the square root of the color of the pixel that where the light exits. So square root multiplied by square root is original value. So we are taking a mixture of the exit point color and the entry point color. Now we're doing this because our setting here has a texturing mode called pre and post scatter. So we are taking some color from pre-scatter and taking some color from post-scatter. Actually, there is a different settings where we can change that behavior, but here, because we're doing pre and post-scatter mode, we take square root when we make the diffuse lighting buffer, and we take the square root when we take the make the after transfer thing. Now, this result is our diffuse lighting in the scene of subsurface scattering pixels after the transfer, and this contains two things. It contains the total lighting of non-subsurface scattering materials, and it also contains the specular lighting of surface scattering materials. Right? We just add those two together, and then everything is done. Voila. Now, the most important part of the surface scattering is this light transfer stage. Here is the code that for each pixel samples the neighbor's diffuse lighting to transfer from. So we're doing a lot of sampling of neighboring diffuse lighting in this code. The code is complex with a lot of tricks. We're doing LDS caching. We mentioned LDS caching last talk. It's a local data storage caching in the compute shader unit. And we also do importance sampling so that we sample a bit less. We don't really sample everything around. We sample only important parts that's representative of the surface. Okay, so before we do closing remarks, let's actually do this GPU capture of our final frame. Cool. Okay. So the first thing to note is when we are doing the GBuffer pass at the very end, after we've done all the GBuffer pass, the stencil is a little bit different. It's not so obvious, but this gray is a little bit different from the other grays. This is actually the split lighting flag being done. That's making this stencil different from the others. This instructs HDRP during deferred lighting calculation to output the diffuse at a separate buffer so that we can do energy transfer of the separate buffer and then recombine. These are all the same things. We do SSAO, SSR, we make the light list, we loop through each shader variant of the lit shader. Each lit shader is responsible for drawing different tiles. Now, if we look at one example of a shader variant of the lit shader, so here is some example where it's only drawing to one final buffer. Right? This compute shader is doing lighting calculations and outputting the result to render texture UA. This is our usual destination for deferred lighting calculation. But there are also some other shaders. This is a particular instance of the lit shader that supports subsurface scattering, and this is in charge of rendering a number of tiles where there exists materials that has subsurface scattering. And this shader not only outputs to our usual render texture UA, it also outputs to this camera SSS diffuse light guy, and this is outputting the specular lighting to our usual camera color. Oh, sorry, I said camera texture UA. This is not called camera texture UA. It's called camera color. Sorry. Okay. So usually the shaders output to camera color, but this shader variant of the lit shader outputs to two render textures. It not only outputs to the camera color, it also outputs to the camera SSS diffuse light. And this is, you can see, this is a little bit white because it's only taking the square root of the color. And it's doing it, you can see like a very sharp edge, right? So it's not only the tile that's constraining the shading, it also looks up the stencil buffer for split lighting flag. And then here is it completed. So the subsurface scattering supporting shader shades everything in between these two passes. And after that, this H-tile pass and this subsurface scattering MQ compute shader together, this is our energy transfer process. After the process, this pixel shader, this is called combined lighting, right? It's taking the original. This is taking the our pixels with subsurface scattering's diffuse color. After the energy transfer, taking that and adding that to our camera color result. And so here is our final guy. So, yes, closing remark. So this is only a small part of HDRP. We didn't cover emissive lighting. Emissive lighting has some complications with indirect diffuse lighting. We encode emissive along with diffuse indirect in the same Gbuffer. So we calculate the final lighting that's supposed to be there from indirect diffuse and add emissive lighting together. So this kind of complicates the screen space ambient occlusion and everything else. So we didn't talk about that. There is the Gaussian vector and temporal anti-aliasing. So, like when we do temporal anti-aliasing, we kind of vibrates the camera a little bit and and then we keep multiple frames and correct for motion of the camera and motions of objects, and then use the previous frame's result to anti-alias the current frame. This kind of thing, we haven't talked about it. The decal we have is only modifications of color normal, this kind of simpler parameters in the Gbuffer. We haven't talked about mesh decal. Area lighting, there is a lot of innovations in Unity about area lighting in the past. We can do area lighting efficiently with analytical solutions. It's pretty cool. There's volumetric lighting that we have, and we haven't talked about that. Like when you have like a beam of light across the floor, across the atmosphere, and it's like a angel ray, that kind of thing. As we said, in SSS, we've only talked about the actual scattering, but not the transmission part. So when light goes into something and then the back of something and then pass through the object and come out the other side, right? This kind of thing is supported by SSS. We haven't talked about that. There are lots of other advanced lighting models like translucent, hair fabric. We haven't talked about how they work. And we haven't talked about real-time ray tracing. So a lot of things we didn't cover, just to be aware. So for more details about HDRP, you could check out Sebastian's talk in SIGGRAPH 2018 or Evgeny's talk in SIGGRAPH 2018. They are actual authors of the pipeline, which most definitely knows way more than what I do. Yeah, so if there's anything wrong, just email me and I'll check it. Probably there's a lot of things wrong. Okay, finished. What should I do? How? So thanks for watching, guys. And have a good day, guys.